And this video I'm going to show how to use reinforcement learning in Simulink. In this video we're going to use a very simple model just to show how this is done, and it is to control the level of a water tank. We have a desired water level and an initial input water level, and it's going to take the water to the corresponding reference level. This can easily be implemented with a PID proportional integrative derivative controller, as always done, but and probably it's more efficient than reinforcement learning. But again, the purpose of this is just to show how to use reinforcement learning in Simulink. So the environment is going to be the water tank and something else for reinforcement learning, and the PID controller is replaced by the agent. So this is going to be the agent. And in addition to the water tank system, which is exactly the same, we're going to see a subsystem to compute if the model stopped or not, a reward to compute the reward, and also to generate the observations. And that is going to be used in the agent, which is going to be MATLAB based. Inside of it is using a MATLAB system object. It's a mask subsystem. So the agent that we're going to use is going to be a DDPG agent. The nature, the observations that we're going to get in here are the water level, and the error, and the integral accumulative error is this has an integrator, so we're going to provide the same for the agent. So those are all continuous. The action is going to be the flow of water for the water system. So again, that is contiguous. Going as I mentioned in the previous video, reinforcement learning is composed of an environment and an agent, and they communicate through the action and observation. The action and observation can be seen as the API. So based on the observation, the next action is going to be selected based on the policy, and based on the rewards, the policy is improved. In this case, the agent that is going to be used is DDPG. Again, and if you remember this chart, we used Q learning agent last time because we have a Markov decision process that was both discrete in action and observation, so we could take it the most simple. This was just a table. In this case, we're going to have a continuous action space and continuous observation space. So the simplest one is the DDPG. And the DDPG is basically uses deep learning. It's a model-free online. It's called Deep Deterministic Policy Gradient. So it's a little bit more complicated, and as you may expect, it's going to take a little more time to converge than the training the Q table for the Q agent. It takes about 30 minutes or so, but I'm going to pause it when I go to the training. Okay, so yeah, that's what we're gonna do here. So let's go to example, and just click here, and that'll take you to this place. Okay, so let's open the model, which is the water tank model, reinforcement learning water tank model. And let's take a quick look at the subsystems. It's a little bit interesting that, and you will notice that we got an error because we don't have the agent. We're going to create the agent. Once we create the agent in the workspace, this reinforcement learning block is going to look for the agent in the workspace. Once we have it, this is going to stop giving an error. So we have the water tank system. And notice also that we have these displays that are going to show us how the water level increases as time goes by. And you can get those by creating or connecting to an existing scope. You see, you have the scope, so all of these three signals are connected to the same scope, and if you just double click it, you're gonna get the scope. And in here we're gonna get the reward, and we're gonna get the flow, water flow, reward, and also the water level, the height. You can see this is the height in here. We're gonna get those at the end. Let's take a look at the water tank. The water tank is just you have a gain for the flow of water. You have an accumulator, an integrator of the water. This is gonna accumulate the water in the tank, and then you have a difference between the height. The difference between the height and whatever you flow in is gonna determine how the accumulation is gonna go through. Okay, so the stop simulation, of course, if you go above 20, you overfill, so that's a failure. And if you go below 0, it's gonna basically stop giving water, so it's a failure as well. So that those are conditions for early stop. And but no, okay, if you overflow, of course you fail. But yeah, I guess let me see. This is the height. But at some point it's gonna stop because you reach to the point. This is the height, not the difference. So it has to stop also when you reach to the target level, or it might not stop. It just stays there. I think so until the time runs out and you stay in the right place. So I understand that this is just failure mode. Okay, so then you have the reward. The reward you're gonna have, as you're gonna expect, you're gonna have a big failure because of early stopping, and the error, that's the difference between the height and the desired water level. This is, notice that all of this is replacing your PID, the control system. So this is now the difference, and that is gonna provide us for the reward signal, and this is gonna guide how you're gonna change your policy as you train the agent. So if you go out of bounds, you're gonna have a gain of negative 100. So that's a big penalty if you go out of bounds. If the error is below 0.1, this is good. So you're gonna get a reward of 10, which is better than not being, if your error is high, that is common. So you just get a negative 1. So if you take a lot of time to put the tank in the place, then this gonna get accumulated and still it's gonna be bad. Okay, so the observations are basically some manipulation of the input signals. We already get the height as it is. The error, we already get it. So I guess we need the integration, accumulation of error, and for that we have a discrete integrator. And we provide those three, package them into a vector of 3 elements, and that's gonna be fed. So we have a vector of 3 elements, and we have a reward, which is a scalar. Okay, so now we have the model, and the name of the block for the agent is RL agent. Okay, so now the first step is to create the observation. Again, this is like the API between the agent and the environment. So you have this vector of 3 elements, and the first one is the integrated error, the error, and the measure height. The first two go from negative infinity to infinity, and the final one go from 0 to infinity because the water cannot have a negative number. And the actions are simple. It basically is just a scalar, which is the flow of water, and by default it's going to get the range from negative infinity to infinity. Now we're going to create the environment. It's very simple. We just specify the Simulink model and the block. Remember that the block is the block is RL agent. So we're gonna pick up what this is basically the path to the block. It works like a file system, a file path in an operating system. So for example, if you have you want this block here, apps, it's gonna be RL water tank dash calculate rewards dash apps. So that's how you get a block. Okay, and now after you get the block, you have the block of the agent, you have the Simulink model, and the observations and actions, which is the API for the environment. And then you create the environment. Also, for each episode, as in the previous video, you have to reset into an initial state, and for that we're going to provide a function, and that function is going to randomly select the height of the water, the initial height of the water, and randomly select the desired height of the water, and we're going to run that when we train the model. Okay, so I'm going to provide a handle of that function to the environment through a reset function property. We're going to have a time step of 1 and final time of 200. So we're going to have 200 iterations per episode, and we're going to use this for reproducibility of the experiment. And now this agent, this DDPG agent, is going to have a critic and an actor. The actor, each of them are going to have their own neural network. The critic is going to basically predict the value for a particular action at a given state. And the value is the expected return, that is the expected accumulation of reward from that point until the end of the simulation. So it's going to have that's the value, the expected accumulative reward from that point until the end of the simulation. So once you have that network is capable of predicting the value given the state and action, it's going to get the action that gives you the maximum reward, the total reward. And with that, it's gonna basically, and then the actor is gonna also use the observation to determine the action. The critic and the actor, the two play together to select the action in the agent. Okay, so first we're gonna create the critic, and for that critic we're gonna require a neural network, and this, as you expect, the value takes two inputs: the observation and the action, and the output is gonna be the value, which is a scalar. So you have a fully connected layer at the end that returns a scalar. You have two input branches, one for the observation, which has a size of 3, because we have 3 observations, and as you may expect, the action branch is going to have a size of 1. You only have one observation. So the action only has one fully connected layer, and this one has 2 observations. Of a filter size 50, you use ReLU for regularization, and bring it down to 25, because you're gonna add them both together. So when you add them, the size of the networks of the layers have to be the same, so that you can add them, and finally you bring down to 1. Okay, so you create those layers, and then you create a layer graph, and you add those layers to the graph. At this point, they are unconnected, and you can see it in here. I'm gonna just show it so that you can see this connected. You see, you have the observation path, you have the action path, and you're gonna connect this one to the input number 2, and this one to the input number 1 of this one, which is what this is doing, connected to the add path, to the add block. Input number 1 is gonna go through the last layer, this one of the observation, and the second input of this one is gonna go to the FC1, which is the output of the action path. So let's connect them and let's plot it again. Okay, so now we have them connected. So you can also look at like this with analyze network, and we get more detail, and you can confirm in here that you have a size of 3 for the observation input, and for this one have a size of 1. The layers go down from 50 to 25, both become 25. You add them here, and regularization, and you have the value of that state and action for that given state and action. Okay, so with that, we create a neural network, and we get the summary, which is no different from what we saw with analyzed network. Now we're going to create a Q-value function that is going to predict the value. The critic is going to do that. Takes the API of the observation object, the action object, and this is important, the observation input names, because he knows that it's going to use a neural network, and the input for the observation is going to be this one, which is this same name of the layer, and the input layer for the action is this one, which you put it in here, so he knows where to pass the observations and where to pass the actions to the neural network. And now we have the critic that is going to predict the value given the state and action. But now we also need the actor. Well, first we're going to test it. We're going to create a random observation vector. Basically it's integration error, and height of the water. And we're going to create a random action. And now we're going to pass those values to the critic, and the critic is going to give us the value, and that's the expected reward. This is the expected reward, total reward until the end for the given observation and the given action. Now we're going to create an actor, which is a more simple network. Basically, it's just the input is going to be the action. We're going to only have the observation, which is a vector of 3, and you have only a fully connected layer with 3, and then you bring it down to 1 with a tan edge layer, and that's going to go from the action, from the observation to the action, So that's why it's called actor, because it's going to act. The other one is just going to give you a value. Okay, so now here's the network. It's a very simple one. We're going to, and now we're gonna create the actor. We already created the critic in here with the Q value function. Now the actor continues deterministic actor. So the actor network is this one. Again, we pass the API function, the API objects of the observation and action, and we get the actor. And now we're gonna test. We're gonna test a random observation again. This is a random observation, and for that random observation, this is the water flow that is gonna give the actor 0.34. Now we have the actor and critic, and we create the DDPG agent, which needs both the action and critic. So we're gonna create it, and that agent, as you might imagine, needs to train the neural networks, and for that we need to provide the options. So target smooth factor. Discount factor is basically the how much reward you lose across time. Since it's 1.0, that's a value between 0 and 1. So since it's 1.0, there's no loss of reward across time. Still, there's a penalty in the reward of -1 for not being out of range. So still, the more times it takes, it's gonna be bad for the agent. So this is for parallelization. Then you have the variance of the K rate is for the formula of the computations of the reinforcement learning, and then you have the learning rate for the neural network of the critic and the threshold for it, and the same you have also similar different parameter for learning rate for the action. So this one has a faster learning rate. Okay, so once we have the options of training of the agent, we can, well, we're gonna test the agent. We're just gonna provide again a random observation, and the agent is gonna give us the action. But this is useless because it's not trained yet. So that will be a flow of water. So now we're gonna train the agent. We're gonna provide the training options. We're gonna have a maximum episodes of 5,000. Again, the steps per episode is 200. And we're gonna stop on average reward when the average reward is 800 for 20 cycles or so. And now we have the agent, we have the training options, and we have the environment. So that's all we need. So we're gonna do this, and the train is a method of the agent, because we're training the agent. So the agent is in control in here. So yeah, it's a method. So we're gonna train the agent given the environment and the training options. So this is gonna take a while. I'm gonna pause in a moment. I'm just gonna show the initial. But first, this is the first episode. So for each episode, this is gonna call the local reset function to reset the environment, and this is gonna first get you the block, the desired water level, which is this desired water level. Randomly gonna show a value. It's within range, so it's gonna take it, and it's gonna set the block parameter in the block. So this is simulation input. Okay, the simulation input. So it's gonna set the value in here. So this is part of the reinforcement learning environment. So you're not gonna see it reflected in the model. This is not the. I mean, this is a method most likely of this object. So yeah, so you're not gonna see it. You're gonna see it reflected, but still, it's gonna take effect during the training. So again, you're gonna set the initial height, which is basically in the environment, the height of the water. You have a parameter called initial condition for that block. So you can see that the block is named H within the water tank subsystem, and you just set the initial condition. So again, you choose an initial value of 11. So you want to take it up to 11. This is a bad. I mean, it's gonna stop real fast. Actually, it's the same value. So yeah, if you randomize, if I randomize it again, let me see if I get a different. Well, yeah. So you bring it down. So this might be negative. I mean, the flow is gonna be negative because you want to drain the initial height from 16 down to 11. So this can go in both directions, I suppose. Okay, so I'm just gonna let it go and let it train. So we're gonna see at the end if this behaves correctly and if it is able to control correctly the water. I'm gonna pause this for a moment. Okay, it took 4 minutes and 40 seconds to train, and you can see that it got stuck at some points, even went down and to eventually arrive at 800. So now that we have the agent, actually I did it like this, but uh, no, I think I mentioned already that train is a method of agent. So the training is applied to the agent. But now in the simulation, it's another way around. It's a method of the environment. So you're gonna do a simulation in the environment, passing the agent and the simulation options. That are gonna be the number of iterations, which is 200, and stopping on error. And let's express this in the method format. Yeah, so the environment is going to simulate the agent, and this is going to happen in Simulink. So the Simulink model is going to run, and notice now that before we had the warning, and because we created the agent, we don't get the error anymore. So we're going to see during the simulation, we're going to see the control of the water tank level. This is from the training, so you can ignore that. And now we're going to run it, and we're going to get the experiences. And from the experiences, you can see the list of actions that it took to arrive to the target. You're gonna see the reward for each action, the observation for each action, and if it finished or not for this particular simulation. And you can see when running the model, this I'm gonna make it larger. So the reference here is 13. So let me see if I can control the reference in the simulation. Actually, I can. So I have 10, and the initial state is initial condition is 3. So it has to come from level 3 to 10. So yeah, I don't know why it starts at 11, but anyway, this is the initial state, and it gets to the final point. Notice that as soon as it arrives to the level, it's gonna give the reward of 10. While is you have an error, you have a negative 1 reward. And also notice that the flow is higher at the beginning, but then eventually it becomes very low once it becomes stable and it finishes the simulation. Notice that even though you arrive at the target, you don't stop the simulation. You only stop the simulation if it goes above or below. So let's make some experiment. Let's try as an initial condition. Let's make it negative or 100. So we have a fuel tank, and we want to bring it down to 10. So I want to save them all and run it again. Let's see how it goes. It's a little different. It's coming from 7 this time. It's like I'm not controlling the reference. The reference is supposed to be 10, not 9. So I'm gonna give a check to this to see what's wrong with this. The problem is that the model is not really in control of the initial state and the desired water level. The reset function is on control. The environment is in control of those values through this function, and you're not going to see them reflected in the model. So let's run it again, and let's manipulate those. So it cannot be beyond, the water cannot be beyond 20. So let's put the level in 19.5 or something like that. H equal to 19.5. Okay, and that is going to be accepted because it's within the range. And then for the desired height, we want to, let's say we want to drain it, we want to set it to 0, we want to drain the tank. Okay, now let's run it. Oh, it didn't accept it. Oh no, it took another value because yeah, it has to be a little bit higher than 0. So let's put 0.5. Okay, and let's run it. Let's see how it goes. Okay, so okay, so okay, so I think I got it the other way around. Okay, so this is the desired. Oh, I put the desired to be 19.5 and the initial value to be 0.5. So it's going from 0.5 to 19 points. So it's filling the tank. Actually, it's filling the tank. So it works. It takes longer this time. So you can see that you have a high flow field. Okay, stop filling. And then you have the reward. Actually, it didn't get the reward because it just stayed there, and the difference was not enough to get the reward. That's kind of weird. But let's say if we try another one. Let's just play with integers. I'm gonna put a couple of breakpoints. Okay. H equal to 19, and then run it. H equal to 1. Whoa. Okay. Run it. Nope, no reward. Let's try again. Okay, just let's put H equal to, let's say 18, and let's take a closer value. H equal to, let's say 15. Yeah. Well, now it's closer. It's closer, but still, I don't see the reward in there. Okay, I'm gonna try it again. Let's see something really close. 17, H equal to 15. Okay, anyway, now let's check with draining, but at least it's filling the tank. Let's drain the tank. It's gonna be initially in 1. That because that's the desire. We want to drain it. We want to bring it down to 1. So now let's put that the tank has to go. The initial level is 19. Okay, so we're gonna drain the tank. So it does work. I mean, it brings it down. The flow is negative, so you have a negative flow to drain the tank. So it works out well. Something is wrong with the rewards, but at least it's doing its work. Okay, that's it for the video. Thank you very much for watching.